Yep. There you go. So, obviously, scuffed online setup, we use just Microsoft Paint. Sort
Uh,
of. I remember last year when things first went online due to COVID, sort of started using Paint as a joke, and then it sort of stuck with it. Um,
it's
but
a great tool.
yeah, I've gotten this far just literally writing and drawing things with my mouse on Paint.
Oh wow, that's actually pretty difficult.
Yeah, and you can definitely see like over the course of a semester if you because I'll post like the images afterwards in session docs for most of my sessions. You can see like a gradual improvement in my
Yeah.
handwriting, and then like I'll go a month and a half not doing it over winter break or the first part of summer, and then it's like back to being garbage.
Uh, yeah,
But
that's funny.
but let's just start. Let's just hop right in and get going. So, first thing I want to know is what exactly is momentum? What is your best interpretation of what momentum is?
To be honest, I'm not sure. Like I'm honestly like I honestly can't say. Like,
So, so is
yeah, go.
there an equation for momentum that you know?
Um, Not off the top. Like that's what I'm saying. Is really I've been extremely busy, so I kind of just been like
Okay.
finessing my way through the last week.
So essentially, momentum is a way of. I mean, I'm curious. What does Google say? Momentum definition: the quantity of motion of a moving body measured as a product of its mass and velocity. So essentially, momentum, which we usually define, it's usually a p, and we usually it's a vector, so we add a little arrow thing.
Is- Hold on a second. I'm probably going to be asking a decent amount of questions, so I'm
Mm-hmm.
sorry if I talked to you a bunch.
That's fine.
Um, that that physics 121 equation sheet that's on the course page.
Yeah. So, um, for some reason, it's weird. It's I maybe I should actually bring it up to him. As I noticed this. I don't know if anyone else noticed it. So, yeah, you go to the course page, and for some reason, so you go to course materials, and it's not here under course materials. It's inside the class one folder.
Okay,
Um,
that's because I was looking for an equation. I was like, there's no way that we was thinking an equation sheet for this.
yeah, for some reason it's just sitting in the class one folder. Um, it probably should just be in the course materials generally, but yeah, you can find this whole equation sheet on there. And
That's awesome.
that's another thing I recommend for this class, like, and for like if you take 122 in the future, nothing in physics really makes conceptual sense, or it's difficult to really conceptually understand what the hell's actually going on, especially once you get into physics 122, but even still in 121. So things don't really make sense. But what does make sense is the math. The math
Yeah.
usually isn't too overly complicated. As long as you've taken Calc 1 and maybe a bit of Calc 2, you're usually fine. And as long as you can solve the math, you're usually good. So, um, do you have any other questions?
No, that was it. I was looking for that equation sheet. I knew I
Okay.
had.
Yeah. So, with the equation sheet, how can we describe momentum?
So
This.
it's mass. So it's total mass, and it's a vector quantity.
Mm-hmm.
It's 20 times velocity.
Exactly. So it's going to be the mass times a velocity. So
Direction of the velocity.
exactly, the momentum is in the direction of the velocity. So that's what momentum is. And so essentially, as something is moving along, it has momentum. If something's heavier, it's going to have more momentum than something that's lighter if they're moving at the same speed. And two objects of the same weight, that's the same mass, or the one that's moving faster is going to have more momentum. It's sort of a way of quantifying like the amount of movement energy it has, though that actually is a different thing. It's sort of weird to conceptualize it, just know it's mass times velocity. And so, do you know what an elastic or an inelastic collision is?
No, I don't.
Okay. So imagine you have a block that's just sliding along. Let's say there's no friction. It's sliding along, and there's another block that's not moving. They go ahead, they're going to ram into each other, and they're going to stick together and both continue sliding along. Are they going to be moving at the same speed that the initial block had? Are they going to be moving faster, slower?
They would be moving slower because there's more mass.
With more mass, so what quantity is conserved?
Um, the quantity is conserved. Oh, well, would momentum be conserved?
Exactly. Momentum is conserved because the blocks are essentially they're moving along and they stick together, and they're going to end up moving slower because there's more mass, and we know that momentum is always conserved. So there's some examples where actually if we go ahead and calculate this, let's use some numbers real quick. So let's say it's just 1 kilogram and also 1 kilogram. We'll keep it simple. And it's initially moving 5 miles an hour. What is the initial momentum of the entire system?
It'd be 5. Is there like a is there like a is there like units for it?
No, there's not a specific name for the units. So, but what would it be in terms of the units of mass and velocity?
8 kilograms per meters per second, or it'd be 10 kilograms per meters per second.
Not kilograms per meter per second, it's just kilogram meters per second.
Kilogram meters per second.
Yeah. So, and now what would the final momentum be after the two blocks collide?
It'd have to be the same. It'd have to be 5. So does that
So what would the velocity be?
the velocity would have to be it would go to 2 to 5 divided by 2, which is 2.5.
Exactly, 2.5 meters per second. So they collide together and they have a final velocity of 2.5 meters per second. Now, do you know what kinetic energy is?
Yeah, kinetic energy. Well, kinetic energy is the. Hold on a second. Yeah, well, kinetic energy has to do with. Kinetic energy has to do with anything that's moving compared to with potential energy, which is just from the height of an object.
Mm-hmm. So how do we?
Yeah.
What's the equation for kinetic energy?
1/2 mass velocity squared.
Exactly, half mv squared. So what's the initial kinetic energy of this system?
It would be velocity is 5. It would be 2.5 joules. 2.5 joules.
2.5 joules?
Yeah. Because there's no velocity on the second object.
But it's velocity squared.
Oh, it's velocity squared. Good point. Should be 12.5.
Yep, 12.5. 25 over 2. So that's the initial. What would the final kinetic energy be?
It'd have to be the same.
Is it? Go ahead and calculate it.
I think it will be, but let me just calculate this. So the final kinetic energy is, I believe, if I did this right, in terms is 6.25.
Sorry, what was that? Your
Six.
mic is like cutting in and out.
Sorry. Can you hear me now?
Yes.
6.25 would be the final kinetic energy, I believe.
Yep, exactly. It's 2.5 squared. So that's not the same, right?
No, not at all.
So this is a collision, where the two blocks collide together and they stick together and continue traveling. The momentum is conserved, but the energy is not. This is what's called an inelastic collision. In fact, this would be a perfectly inelastic collision.
Why would it be perfect?
Because the objects stuck together. That's the definition of a perfectly inelastic collision. It's when the two objects stick together.
Momentum conserved, kinetic energy is lost.
Yep.
And this is an inelastic collision.
Yeah, perfectly inelastic. You can have an inelastic collision where they don't stick together. So, for example, if they collide and the one block takes most of the velocity. So, for example, this block would continue traveling along. Sorry, what was that?
That's what it is, right? Is that the fact that since momentum is conserved, then when two objects come together, they're just transferring velocity. Since mass goes up, that one of them has to be taking the velocity from the other one, equal proportion. Basically, if that makes sense.
Somewhat. So
yeah.
So a perfectly inelastic collision is when the two blocks collide and they stick together, and obviously the kinetic energy goes down. So an elastic collision would be when the two blocks collide together, and then not only is the momentum conserved, but the energy is also conserved. Do you know how that would maybe happen here?
Elastic collision is when energy is also conserved and momentum is conserved?
Yes.
Okay, I'm just writing this down. Cool.
So obviously for an elastic collision, the blocks are not going to stick together. Mm-hmm. Do you know what the collision would actually look like if it was completely elastic?
Momentum has to be conserved. Does that mean that momentum has to be split between the two forces? Because how is it when you say the system, it's momentum of the system, correct?
Yes.
Okay. So that would mean that I would say the mass wouldn't technically change, which means the velocity wouldn't change. So I'd say maybe that and they have to be coming at each other from different sides. Like they have to be basically like at each other from opposite vectors.
Well, the first block is moving. The second block is not moving initially.
The second block is not. Yeah, I'm honestly not sure how momentum and energy would be conserved in that case.
So let's go ahead and we can actually solve for it. So let's say initially we have the masses and we have the initial speed, and let's say afterwards we have the first block. Afterwards, we're going to have the first block traveling at a speed v1, and the second block is going to travel at a speed v2. So we need to find a way to solve for v1 and v2 so that the total, and we'll call this initial velocity up here v naught. So we have to find a way such that half m, I'm just going to add them together because obviously it's half m v1 squared for the first block plus half m v2 squared. I'm just going to write that together as half m v1 squared plus v2 squared. We have to find a way so that this is equal to half m v naught squared, the total initial energy of the system. Right? So how could we solve for v1? What are our options for values of v1 and v2?
Just writing down.
And there's one other equation we'd have to write down.
I'm not sure what exactly.
So
I mean, I mean, the only one I can see is if not.
So this here is conservation of energy. What's the other
Yeah.
thing? What's the other thing being conserved?
If you conserved momentum,
Momentum. So what's the equation for the conservation of momentum?
mass time velocity.
Exactly. So the initially we have mv naught, right? And what's our final momentum?
Mass time.
Times, so it's mass times v1 for the first block,
Yeah.
plus mass times v2. So m times v1 plus v2. Right? So
Yep.
let's go ahead and simplify both these equations. Mass cancels out for both equations, and the 1/2 also cancels out. So we know that v1 squared plus v2 squared has to equal v naught squared, and also v1 plus v2 has to equal v naught.
Yeah.
So how do we make it? So what values would work so that these two equations are both equal?
Yeah. V1 and V1 and V2 can both equal something different. Not see. Hold on a second.
What if maybe one of them was 0?
Yeah, that's. Well, yeah, V2 has to be 0. Or, I mean, in this example, V2 has to be 0. So, yeah, V2 had to be 0, so V1 would have to equal V naught.
Exactly. Or actually, it'd be v1 is going to be 0, and v2 is equal to v naught. Essentially, what's happening is we have our two blocks, and we have our first block is traveling along. It's going to boom. It's going to collide with the second block, which is then going, and then the first block is going to instantly come to a stop, and the second block is going to start traveling along with that exact same initial speed.
In what case would that? I mean, is that? I mean, like I understand how that works, but
so
does that happen?
What was that?
Does that ever happen?
Well, this would be a perfectly elastic collision.
Perfectly elastic.
So, essentially, an inelastic collision is any collision where energy is not conserved. A perfectly inelastic collision is where they stick together after colliding. And a perfectly elastic collision is where energy is conserved.
What about just an elastic collision?
Well, that there is no. I mean, an elastic collision or a perfectly elastic, it's the same thing.
Same thing.
So essentially, like if we have like a spectrum of different types of collisions, where we have elastic or perfectly elastic at the top, and then perfectly inelastic at the bottom. Everything between can be described as some sort of inelastic collision.
Okay, so basically almost everything is an inelastic collision.
Mm-hmm. So that's the main things you have to understand. So momentum is always conserved, and then based on the elasticity of the collision, energy may or may not be conserved. So might be a bit much to understand, but honestly, the best way to do it is to let's just actually hop in and do this example problem here, which we've actually sort of mostly done, but let's just run through it again, and I'm going to try to not help you as much. So,
Definition of this sentence.
So we're going to have two blocks of equal mass, and in this case, we're not going to have one at rest and one actually traveling. Both blocks are going to be traveling in opposite directions with equal speed, and they're going to collide with each other. So this is going to be V, and be V, and they're both M.
Right. So what is the total initial momentum of the two block system?
Mm-hmm.
It would just be 2m 2v, but 2m times 2v.
Mm-hmm.
Actually, because velocity is a vector quantity, wouldn't the velocities cancel each other out?
So what's the total momentum of the system?
It would have to be 0.
0, exactly. Boom. And you're exactly right with the fact that velocity is a vector quantity, so momentum is a vector, and because the velocities are opposite, the momentums are opposite, and therefore the net total momentum of the system is 0. So what's the total initial energy of the two blocks?
Total initial energy would just of the two block system. So I want to say that it's just mass times velocity squared.
And how did you get that?
Because it'd be 2 mass times 2 velocity squared. The 1/2 will cancel out with the 2. Because energy, it would just be kinetic energy. Energy isn't quantity. Even if the velocity was negative, it would turn into positive with the square. So the total kinetic energy has to be the kinetic energy added, both of the blocks added to each other.
Mm-hmm. So essentially, it's half mv squared for the first one, and half mv squared, and so they add together just to equal 1/2 mv squared. Yeah. Sorry, 1 mv squared, not. So yeah. So momentum is equal to 0, energy is equal to mv squared. So what's going to be the final momentum of this system?
Well, given that momentum is conserved, it would be 0.
Exactly. Momentum's going to be 0. But if
momentum always conserved?
Yep. Momentum is always conserved for every single collision ever. If I throw a ball at the ground and it bounces back up, the energy that was, or if I throw a ball at the ground, or like not a ball, something sticky that's going to stick to the ground, I throw it down as hard as possible, the momentum of the ball is transferred into the Earth. And if I do that enough times, maybe a few million times, I can throw the Earth out of orbit. Not actually, but because...
Yeah, no, I get it. That's good. That's classic.
But, so the momentum's always conserved. But also, essentially they collide and then they travel away from each other with v over 2.
It will be traveling away from each other with v over 2.
So yeah, same thing. If you were to actually calculate the momentum, the velocities are still opposite to one another, so the momentum would be 0.
And how would you calculate that it would be v over 2?
Well, I'm just saying that's what we're saying here is the blocks are rebounding off each other with
Oh,
speed equal to half of what they had before.
okay, nice.
Yep.
Cool. Let me get it.
So what would be the total final energy of the two blocks?
Um, it would be the same as it was before because, well, actually, I'm just kidding. It'd be less because the kinetic energy has been lost because velocity has been cut in half. So, to put that into an equation, it would be. I mean, couldn't you just say it'd be m over? I have to actually do this out.
So what's the energy of the first block?
The energy of the first block is mv over two is 1/2 mv over 2 squared.
Mm-hmm.
So the energy of the second block is 1/2 v over 2 squared. So wouldn't it just be 1/2, or I mean m would just be mv squared. There has to be a 2 to compensate. Something has to be over 2 to compensate for that loss in energy. So I mean, couldn't you just say that it's 1/2 mv squared, basically?
It's not half, it'd be 1/4 because the v over 2, the over 2 squares.
Yeah, okay.
Yeah, it's not v squared over 2, it's
It's v over 2 squared.
v over 2 squared, which then becomes 1/4.
Okay, yeah, that makes perfect sense.
So that is the final energy. So what kind of collision was this?
This is a inelastic collision.
Inelastic collision, because we lose energy. Is it a perfectly inelastic collision?
Uh, no, it's not because they didn't stick together.
No, exactly. And in fact, the the perfectly inelastic collision where they stick together, not only is it like obviously they stick together, and any collision you see, if it's perfectly inelastic, they stick together, but a perfectly inelastic collision is the type of collision that gets rid of the most amount of energy. Like the most amount of energy is lost. So
The inelastic collision, the most amount of energy.
so if this was a perfectly inelastic collision, what would be the final velocities here? Instead of v over 2, what would it be for these blocks?
So it's perfectly inelastic. Well, it would be 0.
Exactly.
They would both be coming at each other, and then like you would have no vector. You have no vector direction just to go.
Exactly. They collide together and they stick to one another, and the momentum is conserved, right? Because initial momentum was 0, final momentum is 0, and the energy, the max amount of energy, is lost because all of the energy was lost.
Because all the energy is lost.
So we said it was inelastic. Honestly, this handwriting is better than me in 3rd grade. So that's something.
Yeah, I was gonna say it's not looking that bad.
I've definitely got it better. Like towards the end of the last few semesters, towards the end of every semester, it gets crispy clean. Like honestly, better than my actual handwriting.
And you're using like a pointer mouse or like one of the ones with the thumb rotation?
Yeah, I'm literally. I mean, I can. Do I actually? Oh, it's not going to work right now. I was going to say I could actually yeah, but it's literally just a basic Logitech mouse that I'm using on a mouse pad.
Yeah. Okay. Cool.
But yeah, so that's this whole example where essentially we know that the momentum is always conserved. Energy is not necessarily conserved, and because we know we're losing some energy, it's an elastic collision. But because there is an example where there could be more energy lost, it's not perfectly inelastic.
This might be a little bit of a interesting question, but if the energy is is energy always conserved? Not necessarily collision, but where does the energy go in this case?
I mean, it can go. We sort of, for this class, we're hand waving it. We just say that the energy is lost. It's usually
Yeah.
lost. It's lost in the form of heat. You know, if it's like friction between the two blocks, or if
Yeah.
it's sound, like the sound of two things colliding together. That's energy that's
Oh,
being lost. Stuff like that. It's usually heat or sound. Um, do you have any other questions about this?
no, I'm ready for the next one.
All right. So now we're gonna actually use some values here. I know some students really like using values because they like actually get to calculate things.
Yeah.
Um, so I guess like some students just feel like they just have an aversion to leaving things in terms of letters.
I
And
actually like kind of like that because it's more. I feel like kind of more difficult to do sometimes.
yeah, I prefer the letters, but I'm also biased because I'm a physics major, and I didn't see a single number in any of my classes for the entire last 3 years of my degree.
That's dope.
But so let's go ahead and hop into the next one. So we're gonna have a block with mass 1 kilogram. So we have our beautiful, gorgeous block. Is gonna start at the origin, so just x equals 0, with an initial velocity of 25 meters per second. And I neglected to say a direction, so we're gonna say it is to the right. Oh yes. Okay, so we're gonna say it has an initial velocity v naught is equal to 25 meters per second, and mass is equal to 1 kilogram. And this is x equals 0. So we're going to have a second block with mass 2 kilograms. We have a nice big old chunky block at x equals 3. M is equal to, we'll call it M1, and M2 is equal to 2 kilograms with an initial velocity of 5 meters per second. So actually this isn't going to be, please work. Come on. Okay, that works. Just got rid of it. So we'll say it's V1. I literally just shrunk it into oblivion. It's still there, it's just flat. So we have V2 is equal to 5 meters per second. Oh, let's not write the units, just to keep everything clean. So the blocks are going to collide completely inelastically.
Does that mean perfect?
So they're going to lose the most amount of kinetic energy.
So completely inelastically means that they're doing a perfectly inelastic collision.
Yes. So they're going to. So after they collide, then friction is going to apply. So we're going to say before they collide, there's no friction, and after they collide, then there's going to be friction with the ground with a coefficient of 0.2. We're going to keep things simple. So first thing we want to know is, at what point do the blocks collide with each other? And we're going to assume that it's like the blocks are like point objects. So it's not like, we're going to assume they start 3 meters apart from one another. So like this would be x equals 0 and this would be x equals 3.
Okay. So to set up the equation to figure out where they collide with each other, you basically just have to put I mean, what's it just be 25? I mean, I want to just do this in my head, but I'm trying to actually put together like a decent equation.
Yeah.
Figure this out.
So what unit do we have to, this is sort of a throwback to an initial unit.
Yeah.
So what equations would we use to equate the distances? So do we find what point they collide?
Well, distance equals velocity times time, correct?
Mm-hmm. So we have
Uh,
well, so we have
so you,
x is equal to velocity times time. I'm just writing down what you're saying. Go ahead.
yeah, and so would you have to set? Well, you could also use hmm, you'd have to set the distance would have to be equal to one another.
Mm-hmm.
Um, and the distance for the second block being M2 as an initial start of 3. So whatever the equation is, it's some sort of like distance block 1 equals distance block 2 plus 3, I believe.
Mm-hmm.
Um, there's no time in the equation, so that gets rid of all those ones. Um, the acceleration doesn't seem like it has any acceleration. So would you not, and it doesn't seem like it's gained velocity, well, yeah, it doesn't have any acceleration. So would you just do v squared equals what? Uh, huh. I'm honestly not sure what exactly you do. I mean, if I just,
Well,
yeah, go ahead.
you're trying to find an equation that doesn't use time because you're just trying to find the distance.
Yeah, exactly.
But I would recommend maybe think why wouldn't we want to worry about time? Why don't we solve for the time they collide and then use that time to calculate the distance?
Uh, that's an interesting way of thinking about things.
So
Okay.
so you mentioned something about these being equal, right?
Yeah,
So we'll say so we
distance
have
has to be the distance has to be equal because they collide.
so so this is for block 2 and then for block 1 it would just be our initial x value would be 0. So it'd just be v1 times time, right?
Yeah, so x x meaning the final distance where they collide equals x0, right?
Mm-hmm.
Plus v2 squared. V2 or not v2 squared, sorry. V plus time equals v1 time. Uh, I'm trying-
So we just move this over to the right side.
yeah,
And then we can simplify this by saying v1 minus v2 times time, right?
yeah.
And then we
Yep.
just divide to find the time.
So it's 3 over 3 over 20.
Yep, exactly. So the time they collide is 3/20th of a second, or whatever, 0.15 seconds. So what x value do they end up colliding at then?
You just put the you just put the time back into that equation
Mm-hmm.
and you get 25. So 25 times 20. 3.75 meters.
3.75. Yep. I'm going to leave it in a fraction. It's 75 over
Yeah.
20, which is simplified
Yeah.
to 15 over 4 meters.
Okay. 1 second. Let me just write this off. I'm not gonna. I just need to write down that.
You got everything written down?
Yeah.
All right. So Now we're going to go ahead and ignore B and D here, because that would be assuming their friction is acting on them before they collide. We're first going to solve this without friction before they collide, just to make things a bit simpler. So what speed would the blocks have just after they collide? How would we solve for that?
Velocity would just add onto each other because it's going in the same direction.
Mm-hmm.
But with mass. Hold on a second. Let me take a look at my code.
So what quantity is being conserved here?
The quantity that's being conserved is momentum.
Mm-hmm. And what kind of collision is this?
This is a perfectly inelastic collision.
Mm-hmm. So what does that mean about the collision? What is it going to look like?
It's going to lose energy.
Mm-hmm.
It's going to lose kinetic energy. But it will maintain mass times velocity, or mass times velocity after the
Are the blocks going to have different velocities after the collision, or are they going to be the same velocity?
They should have the same velocity since the momentum of the system remains the same.
Well, you could have the momentum conserve, but the velocities be different.
The velocities can change. I don't think about this. So the mass stays the same,
mm-hmm.
right? Well, would the mass stay the same?
Yeah. The blocks aren't grinding away on the ground, slowly losing mass.
Slowly losing mass, yeah.
These blocks, if anything, are going to cultivate mass. They're not going to lose any. Yeah.
Well, that's what I was thinking. Like, but the mass of the system would stay the same because there's been no loss of mass.
Exactly.
Gain mass.
I think I'm confusing you slightly. I think you understand it, but you're just missing one key word I'm looking for. The blocks are going to stick together when they collide.
Yeah, so it seems like they are coming. It seems like they would be gaining mass and therefore losing velocity.
Mm-hmm. Well, for the first one. For the second one.
First one.
So how do we write our conservation of momentum equation? What's the initial momentum of the system?
Initial momentum is mass times velocity. Here's where I'm overthinking. Like, I know I'm overthinking because I know that this problem is a lot more simple than. So when we say momentum of the system,
I mean, like, the total momentum of the system is the momentum of each individual part of the system added together.
Okay.
So it's M1v1 plus M2v2. And we could add the vector quantities, or we can just understand that it's all in the positive x direction.
Yeah, positive x direction.
So that's the initial momentum. What's the final momentum?
So you'd have a new mass, but it'd be the same. So it'd just be M1. It'd be the same.
M1
plus M2.
M1 plus M2, exactly.
And M1 plus M2 times just one velocity, since they're moving at the same.
Exactly. We'll call that V final. So then we just solve for this final velocity, right?
Yeah, exactly.
So V final is going to be, 25 times 1, so 25, plus M2, which is 2 times 5, which is 10, 35 divided by the total mass, which is 3. .35 over 3 meters per second, or 11.667 or whatever it rounds to.
Yeah. So one of them gains velocity, the other one loses it.
Exactly.
Yeah. Okay. Yeah. Okay. That makes. Okay, because the total velocity of the system isn't 30 meters per second because they're not
Yeah,
just because it's quantity, they're not like adding on to each other.
yeah, because that they wouldn't be able to do
Made
that
no
because
sense.
then that wouldn't conserve momentum.
Yeah, for sure. Yeah, that's where I was getting it mixed up.
So, how much
Yeah.
energy is going to be lost during the collision?
Um, well, you just calculate kinetic energy beforehand and just compare it to kinetic energy at hand.
Mm-hmm.
Um, so let me just do that real quick.
So, what's the initial kinetic energy?
Initial kinetic energy would just be mv squared.
Are the masses and velocities the same?
No, that's why it won't be mv squared. It would be well, it would be half mv squared plus half m1 v1 squared plus half m2 v2 squared, and then equals half m1 plus m2 v3 or vf squared.
It's not equal because it's an inelastic collision,
Yeah, it's not equal.
but
Good
that would
point.
be the final. Okay, final is equal to
Yeah,
half.
and then you just subtract final from initial, or you subtract initial from final, and you get the rules.
Yep, exactly. So we can go ahead and calculate both of these. Um, and we can do that real quick. 0.5 times 1 times 25 squared plus 0.5 times 2 times 5 squared. Initially, we have about 337.5 joules. Afterwards, we have 0.5 times 3 total times 35 over 3 squared. So we have a final of about 204.2. So in the total kinetic energy lost is about 133 joules. Does that make sense?
Makes perfect sense.
So then we're going to go ahead and have the blocks sliding along, and friction is going to apply. So just throw back to to a previous unit. How far are the blocks going to slide before coming to rest?
Well, you know that the final velocity is zero.
Mm-hmm.
So you know that kinetic energy at the end is zero.
Yep.
So you just basically be comparing. Uh, you know what the how much what points into rest. So you're looking for a distance.
So hold up. So I'm just going to write down. So you said final velocity was 0.
Yeah.
Initial velocity is equal to 35 over 3. You said we want to find a distance, so we'll call that delta x
Yeah.
equals question mark. What are our other
Yeah.
two? What are our other two kinematic variables?
You have the force of the kinetic. The force of the friction.
That's not a kinematic variable, but we will use that. Just you're getting one step ahead.
Oh, force of kinetic. Uh, sorry. What other kinematic variable do we have? Um,
It's from the first unit.
um, what it? I mean, what is it? I really don't know.
It's all the quantities used in these equations right here.
So it'd have to. Wait, which one? Sorry, I was looking at the.
These equations here,
You could
the
have acceleration.
acceleration, and what's the last one?
It would a time.
Time, exactly. Do we know anything about time?
We don't know anything
We
about
don't know
time.
anything about time, and it's not really useful to us. Do we know what the acceleration is?
Uh, well, we don't know what it is at the initial point. I'm sure we could figure it out.
How could we find the acceleration?
Well, you just do You would you be able to figure it out? I feel like you could use for the force equation.
Yes, yes. So what is it?
F equals mass times acceleration.
Mm-hmm.
F net. And
So,
since you do kinetic energy, then you could use work
mm-hmm.
net, since work net equals the change in kinetic energy.
Mm-hmm.
And work equals force times distance.
Exactly.
So work equals force times distance. You don't know the distance. Wait, so I just got lost a little bit. So are we trying to calculate that acceleration at the exact point where they collide?
So let's put it this way: there are
Yeah.
there are two ways of approaching this problem. You can either use the kinematic variables and say, okay, acceleration is force divided by mass, which we know. We know what the force is?
Uh, I'd say the force is zero, since there was no acceleration to begin with.
Well, we're saying after they collide, then there's friction.
Yeah, so the force would have to be negative.
Mm-hmm. And what would be the value of the force?
It would be the normal force times the kinetic. It would be the normal force of the mass, which is mass is 3, I believe, times 9.81
Mm-hmm.
times zero point 0.4
How did you get 0.4?
or 0.2
0.2. Yeah.
for-
So it's I'm going to leave it in terms of the variables. So we have mu k times mg, and we know it's going to be acting against velocity, so we'll put a negative sign out front.
Yeah.
So we can either use the acceleration is equal to obviously negative mu k g, and then use a kinematic equation to find the distance. Which kinematic equation would you use?
Yeah, I'd use that one that you have really right there because it doesn't use time.
Exactly.
It's v squared equals usually I would just write that down as v equals. Well, yeah, you'd be looking for distance.
Mm-hmm.
X1 minus x0 is just delta d.
Mm-hmm.
So would you posit x0 as just where the collision occurred?
Yeah, sure.
Yes. So yeah, you just do, well, if you wanted to take that out, you know that v squared equals, so it's negative v, negative initial velocity squared equals 2, or sorry, negative initial velocity over negative 2 acceleration equals distance.
Well, it's not negative to acceleration, but the acceleration itself is negative.
Yeah, that's what I was thinking.
Is equal to delta x, which if we plug in all our values, we have 35 over 3 squared divided by 2 times mu, which is 0.2, times g, which we're going to say is 10. Screw 9.81, by the way.
Times
Jeez.
mass.
But the acceleration is force divided by the mass.
Oh, okay.
The mass actually ends up canceling out. Fun fact.
Yeah.
And so we get a total distance of about 34 meters. So that's one way we could do it. We could also do it with the work kinetic energy relation. What is the work kinetic energy relation?
Net work is the change in kinetic energy.
Exactly. Net work is the change in kinetic energy, and we know work is force times distance. So this force times distance would just equal to
distance equals work over force.
Yep. So the distance is equal to our total work divided by the force. What's our total work done?
It's just kinetic energy, and it'd just be the initial kinetic energy because the final kinetic energy would be zero.
Exactly. And what's our initial kinetic energy?
Well, wouldn't it be 337.5 minus 204.2 because kinetic energy final is right after it would be 204.2, correct?
Exactly. So we just have to divide our 204.2, or I'll actually use all the sig figs. Why not? Because it saves it. Divided by the force. Our force is 0.2 times the mass, which is 3 times g, which is 10. Oh, interesting. We get the exact same thing. Because it's just two ways of approaching the problem. And so obviously how much energy was lost due to friction after the collision?
It would be the same as the initial kinetic energy, which was 204.
Exactly. All of it. Do you have any other questions about this?
Not really.
All right. Well, perfect. Hopefully this helped out a bit with understanding the difference between like elastic and inelastic collisions, and then also with different types of collisions, and also like momentum as well. Any other last questions before we wrap up the session here?
No, I'm all good.
All right. Well, then you should be getting a 12 out of 12 on your quiz tomorrow.
God, I really need it. I'll tell you that. Nah,
Right.
I'm fine. But yeah, thank you for taking the time. I hope. Do people normally show up to these, or you normally have to?
So normally it's Alicia. She online now? She is not, no. But so she usually shows up for the weekday sessions, and then last weekend I had Sam, who's actually online now, show up. But yeah, the most people I've had for any of these sessions is like 2 or 3 for this class.
Okay.
It's usually just me and Alicia.
Okay.
So it's pretty chill. We're just hanging out, working on stuff, taking a look at homework questions, doing these example problems I prep. So it's pretty chill.
All right.
And then
Cool.
122, I have 3 people that pretty much always show up, and it's we got the gang together, and we're just vibing.
All right. Cool. All right. I'll probably start showing up when I can.
Yep.
Pretty busy most of the time, but I took a beating on some quizzes this week, so I figured I needed to step up the game plan a little bit.
Yep. So moving forward, they're usually the same time around 1:15, 1:20ish. Essentially, I finish up my 122 session. I give myself a few minutes to prep something for this class. Though I might be moving the sessions later on in the day because I actually just accepted a job offer, and I'll be starting. My start date is the Monday of the last week of class. So I might be moving the sessions to later in the evening. So if that would work better for people, I might actually start doing the sessions in the evening earlier, before the last week. But
whatever works.
We'll see. I'll poll the class tomorrow. Once you guys are done your quiz, to see if people would like the later sessions or not. But gonna have to figure things out. All right. Well, thanks for coming.
If you don't mind, what do you get for? What are you doing for your job?
I am going to be manufacturing for AstraZeneca.
Oh, really?
Yeah, doing. I think they have a different schedule of stuff. I think right now they're working on asthma treatments and asthma medications. So.
Huh? And you got a physics degree?
Yeah. Thing with physics degrees is it's weird because it's there isn't really anything specific that anything you actually do in physics classes. Are you a physics major? I'm assuming not.
Yeah.
Oh, you are?
Yeah.
Oh.
I actually am a physics major.
Okay, I was gonna say because literally 95% of the people that take this class aren't physics majors, but
yeah.
So with the physics classes you'll take, assuming you stick with the major, you'll see what I mean when you take them. Nothing really seems like it would actually apply for a real life job, apart from actually just teaching the material. Like if you actually go into teaching, it feels like nothing you learn is actually really directly applicable. It's mostly more about people like hiring physics majors because they're able to understand the concepts really well and because they're smart. You are not getting through a physics major curriculum alive unless you're intelligent and you're adaptable and you're a very quick learner. And
Yeah,
people love applying people love hiring physics majors because they know that they're very quick learners. And the reality is pretty much any job you get is going to be not really using anything you used in school. You're going to have to learn how to do you're going to have to be trained and learn how to do the job anyway.
yeah.
So
That's what is your coding what is your coding level?
I mean uh, I took 201 back in sophomore year, and then there's a computational class you have to take for the physics major. So I'd say I'm sort of decent at coding, but not really. I mean,
Huh.
so I wouldn't be able to get a development job, but I feel like
Yeah.
if for some reason
Why would you?
I was hired to do like Python developing, I feel like I could learn and figure it out within a few months.
Yeah, for sure. For
But
sure.
anything outside of Python or Mathematica, I wouldn't be comfortable with.
Yeah, for sure. For
But
sure. Well, that's pretty interesting.
yep.
Yeah, no, yeah, that's pretty wild. No, I've had literally no time to even really like look at the class this week, so that's why I wanted to just get some extra help real
Mm-hmm.
quick.
Yep. I hope this helped out. I will have I record the sessions and I upload them to YouTube and I post them in the session videos if you want to go back and look at it. I will also, I mean, let me do that this right now. I also post the Paint PDFs of everything we went
Cool.
over in the session docs if you want to look at that. But thanks for coming through, Delone.
Yeah, thanks, Dylan. I'll try to keep coming to these as much as possible and get some reps in with you.
Yep. All right. Thanks for popping
I'll
through.
see you, dude.
See ya.
See ya.